And now we have the next topic, wave motion. In this video, we take a look at the concept of mechanical wave. Put simply, a wave is a disturbance that propagates from one location to another. Say you have a system of points, for example, or particles, for example, lying on the x-axis, undisturbed. The x-axis we refer to as the equilibrium position of the particles, undisturbed position of the particles. We introduce a disturbance. The particles are disturbed from their equilibrium position conforming to the shape of the disturbance that we introduced. If this disturbance is moving from one location to another, you have a wave. There are different kinds of waves. One type of wave is the mechanical wave, a wave that requires a physical medium in order to exist and propagate. Without this physical medium, you don't have the mechanical wave. Examples include wave in a string, a wave traveling through a string. Without the string, the medium, the physical medium, without the string, you don't have wave in a string. Sound is also an example of a mechanical wave. Sound is basically a pressure wave. Without a physical medium, you cannot have pressure. You cannot have sound. Water ripple or water wave and earthquake, these are examples of mechanical wave. There are two types of mechanical wave to speak of. You have transverse wave and longitudinal wave. For a transverse wave, the disturbance in the medium is perpendicular to the direction of the wave propagation. An example of a transverse wave is wave in a string. Again, a wave that is traveling in a string. Say you have a string, keep it horizontal, fixed at one end, and we hold on to the other end and vibrate it. Say, vibrate it vertically, up and down. We introduce a vertical disturbance that will travel down the string, a wave in a string. The direction of the propagation, the direction of the motion of the wave is horizontal along the horizontal string. The disturbance that we introduce has the same orientation as the vibration that we use to vibrate the end of the string. The disturbance is perpendicular to the motion of the wave, to the direction of the wave propagation. You have transverse wave. For wave in a string, the speed of the wave propagation, the wave speed, is given by square root of f over mu, where f is tension in the string. For a wave to travel down the string must be under tension. And mu is property of the string, linear mass density of the string. Mass of the string divided by length of the string. Unit for linear mass density is kilogram per meter. Again, property of the string. Each string has its own value of linear mass density. Transverse wave. And for a longitudinal wave, the disturbance in the medium is parallel to the direction of the wave propagation. Transverse wave, the disturbance in the medium is perpendicular to the wave propagation. For longitudinal wave, the disturbance in the medium is parallel to the wave propagation. One example of longitudinal wave is sound wave. Say you have a container. Inside the container, you have a fluid, for example, air. Sound wave is basically a pressure wave. We can simulate a pressure wave by putting a piston at the open end of the container and vibrating the piston back and forth. Because of the piston, we are introducing disturbances in pressure in the medium, in the air. This disturbance in pressure will travel down the medium. The direction of the motion, the wave propagation direction is horizontal. The disturbance is horizontal. They are parallel with respect to each other. You have longitudinal wave. For sound wave traveling in a fluid, the speed of sound is given by square root of bulk modulus of the fluid divided by the volume density of the fluid. Volume density, again, unit is kilogram per cubic meter. Bulk modulus, you'll recall, unit is in Pascal, Newton per meter squared. So, speed of sound in fluid is equal to square root of bulk modulus over volume density. Sound can also travel in solid. If the medium is solid instead of a fluid, the speed of sound in a solid is given by square root of Young's modulus divided by volume density. And again, volume density is mass per unit volume, mass divided by volume of the medium. Speed of sound in fluid, speed of sound in solid, same equation. Just replace bulk modulus by Young's modulus. You have the equation for speed of sound in solid. Longitudinal wave. Here are some sample values for the speed of sound in different media. You have speed of sound in air at 0 degrees Celsius, 331 meters per second. Turns out, if you change the temperature of the medium, the speed of sound in that medium will also change. Say that we change the temperature from 0 degrees Celsius to room temperature to 20 degrees Celsius. The speed of sound in air at 20 degrees Celsius is 343 meters per second. From 331 meters per second, the speed of sound is now 343 meters per second. From 0 degrees Celsius to 20 degrees Celsius. Water is also a common medium. You have speed of sound in water. At 0 degrees Celsius, you have 1,402 meters per second. Change the temperature from 0 degrees Celsius to 20 degrees Celsius. The speed of sound in water changes to 1,482 meters per second. And we also have the speed of sound in seawater at 20 degrees Celsius, 1,522 meters per second. So please take note of these values of the speed of sound. And that's it for now. That's it for our discussion on mechanical wave. In the next video, we'll continue our discussion on wave motion, wherein we take a look at the concept of periodic wave. So again, that's it for now, and thank you for watching.